Okay, we're going to go over a few calculations of how to calculate the energy of an electron when it goes through transitions in the atom. So the first question is two parts. We're going to start with the first part. Calculate the energy required to excite the hydrogen electron from level N1 to level N2. So the N would be the principal quantum number. So you have your nucleus, your first energy level would be N equals 1, and your second energy level would be N equals 2. So this is the formula. The energy of an electron is equal to a constant number of negative 2.178 times 10 to the negative 18th joules times Z squared over N squared. So Z is defined as the nuclear charge, and N would be our principal quantum number. So let's look at this for our first electron, or I'm sorry, our first energy level for N equals 1. I'm going to call it E1. And so I'm going to use the formula negative 2.178 times 10 to the negative 18th joules. And then the first thing I have to figure out is what is Z? What is Z? So this is the format for showing an atom, like hydrogen, with its mass number on top and its atomic number at the bottom. So this would be for the most common isotope of hydrogen with just the mass number of 1, atomic number of 1, like you would see off the periodic table. The atomic number is always equal to the number of protons. So when we talk about nuclear charge, is what Z is defined as, that's going to be the number of protons. Because in the nucleus you find protons and neutrons. Protons are the only thing that have the positive charge, neutrons have no charge. So the number of protons would be defined as the nuclear charge. So that is going to be 1 for our hydrogen electron. So I'm going to put in 1 squared on top. And then we're doing this for the N1 for E1, so I'm going to plug in 1 for the N as well. So 1 squared, which is 1, divided by another 1 squared, also 1, is all 1. So what do you get when you multiply something by 1? Oops, itself, of course. So the answer for the first energy of the electron in N equals 1 is negative 2.178 times 10 to the negative 18th joules for E1. For E2, or the energy level, or the energy when it's in the second energy level, once my electrons transitions out to my outer energy level, we're going to use the formula again, negative 2.178 times 10 to the negative 18th joules. And then I'm going to multiply by Z squared over N squared. So we're still dealing with the hydrogen atom. Z is still 1. So I've got 1 squared on top. Now I'm doing this for the second energy level, so I'm going to do 2 squared on the bottom. So I've got my constant. Show a little more of the steps this time. And then 1 squared is 1, but 2 squared is 4. So I'm going to multiply by a fourth, or by 0.25 times the constant. So my second energy is negative 5.445 times 10 to the negative 19th joules for my second energy. So what this tells me is the energy is when the electron is in the first energy level and when the energy is in the electron is in the second energy level. But I want to find the energy from moving from one to the other. So I need to find the change in energy, or delta E. Anytime you find delta anything, in chemistry anyway, it's always final minus initial. So where did it end up? The final was in the second energy level. And then in the first energy level where it started, that's your initial energy level. So I'm going to do delta E equals my final second energy of negative 5.445 times 10 to the negative 19th joules. And I'm going to subtract a negative, so we know what that does, minus a negative is positive, 2.178 times 10 to the negative 18th joules. So then when we do the final minus the initial or plus the initial, then my actual energy change is negative 1.633 times 10 to the negative 18th joules. So that's the first part, finding the energy required to excite the electron. This question actually has a second part to it. What wavelength of light and portion of the electromagnetic spectrum is capable of supplying this amount of energy? So first I want to carry over my change in energy from the first part of the question. We determined delta E to be a negative 1.633 times 10 to the negative 18th joules. And I'm going to move on from that first part of the question. So when I look at the change in energy formula for the light, for the photon of light, the energy is going to be equal to Planck's constant times the speed of length over lambda, which stands for the wavelength of light. So if I'm searching for the wavelength of light, I'm going to go ahead and algebraically rearrange the formula so that that's what I'm solving for. You can also treat it as solving for x. So to rearrange this formula, I would multiply both sides by lambda to get it up out of the bottom. But then I want to isolate lambda, so I'm going to divide both sides by this change in energy. And so lambda is equal to Planck's constant times the speed of light divided by the change in energy. So now I can start plugging in. Planck's constant and the speed of light are both constants. So Planck's constant is 6.626 times 10 to the negative 34th joules times second. And yes, times. And then we're going to multiply that by the speed of light, which is 3.00 times 10 to the 8th meters per second. And I'm going to divide all of that by our energy, which we solved for in the last part of the question, negative 1.633 times 10 to the negative 18 joules. And let's first look at how the units cancel. I have joules on the top and joules on the bottom. But also within the numerator, I have meters per second. So that's also like on the denominator. So that's going to cancel with the seconds from Planck's constant. So my unit for the wavelength will be in meters. So if we plug this all into the calculator, and yes, it is a lot to plug into the calculator, be very careful with your order of operations. You're going to take Planck's constant times the speed of light, and I would hit enter there, and then divide that by our energy. And so we get a wavelength of 1.216 times 10 to the negative 7th meters. Yes, there is a negative sign here, so you could like mathematically apply that, but let's think about that for a second. Does it really make sense to have a negative wavelength? Not really. So what does that negative sign really mean? It means that was the energy that was lost between the transition, but that doesn't necessarily apply to an actual distance. You can have a negative distance. So we're going to say that basically the wavelength of light is 1.216 times 10 to the negative 7th meters for our final actual practical answer. That's only the first part of this question, of this part of the question, what wavelength of light. Now we need to address what portion of the electromagnetic spectrum that comes from. So for that, we are going to look at a very important table that was part of the first set of the notes, where we're looking at if the electrons return to a specific energy level, then that transition will produce a certain wavelength of light. And so you should have at least the number that the principal energy level that they're returning to associated with a part of the spectrum. For IB year 1, you don't necessarily need to know the series, although I would say just for chemistry in general, it's really good to know. It will come up again. But we need to at least be able to tie the energy level to the type of light. So let's look at our atom diagram again. We had our proton nucleus, then I had my first energy level and my second energy level. And the first part of the question asked, okay, if my electron is transitioned from energy level 1 to energy level 2, how much energy does that take? We are looking at the production of light though. When is light emitted? When is a photon emitted? When that drops back down, which it will do automatically because of Aufbau's principle. Electrons do not want to be in the higher energy level. They prefer the lower energy level. So this is automatic. This will happen. And that is when you would get your photon produced. So where is it returning? Returning to n equals 1. If it's returning to n equals 1, then it's going to be UV light. So that's the end of that question. The last part of this video is a completely separate question from the first set. For this, I'm going to look at the energy required to remove an electron from its ground state. So I'm going to use a version of the formula that we used before, but I do want to walk you through how I derived this to be able to go straight to the change in energy. So when we looked at the formula the first time, we just had the energy of an electron in a given spot, which we calculated with this constant times z squared over n squared. And then we found that for 2 electrons and we subtracted it. Well, if we know we're solving for 2 electrons, can we simplify this equation a little bit more, save us some steps? So the change in energy is always energy final minus energy initial. So if I use delta E is equal to, put this in for my final, negative 2.178 times 10 to the negative 18th joules, and I use little subscripts F on my Z and F to represent final. Don't forget that those are squared. Then I can subtract, so that was all for E final, right? Then I can subtract the same thing for E initial, negative 2.178 times 10 to the negative 18th joules times Z initial over N initial, again squared. So looking a little cumbersome, just kind of showing you how that would look with simple substitution. But so let's factor out this negative 2.178, this huge constant, and put it just at the beginning. That's going to be a lot easier to use. So I'm just going to put in parentheses, negative 2.178 times 10 to the negative 18th joules, factored out. So then what's left is that I still have Z final over N final squared minus Z initial over N initial, again squared. And you can treat this as Z over N and square it each time, but don't just put the square all the way on the outside. That doesn't work correctly with the subtraction. So be careful there that you don't mess up the order of operations of that. I'm going to leave it just like this. It's going to make the next part a little bit easier to explain. So we've got our constant times Z final over N final squared each minus Z initial squared over N initial squared. That's my formula I'm going to start with. So let's talk about some of the variables that we have in this equation, because there's not really any numbers here. So how are we supposed to calculate something when I have no numbers? We've got to figure some of those numbers out, of course. So we talked about Z already. Z is known as the nuclear charge. So what's in the nucleus is our protons. That again is going to be my atomic number, which is the same as the number of protons. And so that means that Z equals 1, because again, I'm dealing with hydrogen. So let's talk about the initial and final principal quantum numbers if we are removing an electron from the ground state. So initial would be where it comes from. So that would have to be our ground state. So those are the key words for an initial, ground state. So let's look at the electron configuration for hydrogen, just simply 1s1. The large number in the electron configuration is the principal quantum number. So that would mean n equals 1 initially. Finally, where does it end up? Well, it is completely removed. So what does that mean if it's completely removed? It has gotten so far away from the protons, the nucleus, that there is no attraction there anymore. It is outside. It is indefinitely far away, too far to feel any kind of attraction. So this is going to seem a little bit weird, but for n final, I am going to use infinity because it is infinitely far away from the nucleus, too far to be felt. So I'm going to transfer these numbers. Z equals 1, initial n equals 1, and final n equals infinity. This is going to work itself out with the math. Don't worry about it for right now. So let me start by plugging in to the equation. Negative 2.178 times 10 to the negative 18th joules times, so z was 1, so I'm going to do 1 squared on the top. Final was the infinity, so infinity squared is really infinity. And then z squared, again 1 squared on the top, and on the bottom the initial n1 is 1 squared as well. So starting to calculate some of this out, I still have my constant. So let's talk about this. If we have 1 squared, that's 1. And if I divide that by an infinitively large number, that is squared. So an even greater infinitively large answer, if it's even a thing. Basically, 1 divided by something that is so incredibly large would be something so incredibly small. What's the smallest number I know? 0. So then 1 squared divided by 1 squared, like we had before, is just 1. This is important that it's in the right order, final minus initial, because look what this does. Basically, I'm multiplying by a -1 here, and so my final answer is going to end up as a positive 2.178 times 10 to the negative 18th joules. So the energy required to remove an electron from the hydrogen atom is 2.178 times 10 to the negative 18th joules. It makes sense that this is positive because it's the energy required to remove the electron. This is a very important definition. If I am removing an electron, this is the energy to remove an electron. That is known as ionization energy. So we just calculated the ionization energy for